Hey guys, you got Nick Berry here from Seed Terminator. Just wanted to do a bit of a chat about the Kondinin research report on harvest weed seed mills, the testing done by SAGIT with Trengrove Consulting, Adelaide Uni and Kondinin Group. Before I get into this, I think it's probably worth talking about why this testing occurred. So basically, the industry was looking for comparing the different mills on the market, and I've known for a long time that basically each test is kind of unique in the way the results come out, because the seeds that you put in there are kind of unique to the growing conditions that the seeds are exposed to in their life. So if you get one batch of seed and do a set of tests, even if you control the flow rate of the chaff and the chaff material type, and then go and repeat the testing with a different batch of seeds, usually you get quite a different result. So as an extension of what Sam Trengrove and his team did in a SAGIT project to test the Seed Terminator against a bunch of different weed species, we funded some work for him to test the 3 different meal types against annual ryegrass. And to be fair, we copped a bit of criticism about the fact that we paid for the testing and therefore it couldn't possibly be legitimate, which is a little unfortunate because I think it was done really well. And you can find this report at Farming Ahead, Weed Seed Mills Report, Highlights Need for Ratified Protocol. And here's the testing results here in the link. And so basically this testing was done with ryegrass that was purchased from Yankalilla Seeds, which had a seed weight of 2.8 milligrams per seed. And the seed was processed with chaff at a flow rate of 1.5 kilos per second. We tested the mills on harvesters, so put a conveyor belt in the back of the machine and poured material in. There was one other thing that was criticised, was that the Redicop screen had 200 hours of wear on the working side, and basically you pour the material in and process it and collect it in tarps at the back. So obviously this is difficult to do and possibly not the best setup. Ideally you would have a test stand. So that was basically one of the main outcomes, that all 3 manufacturers would provide a test stand and do the testing. These were the results that we got. We couldn't really tell much of a difference between the Terminator and the iHSD. There was a slight difference, but not statistically significant. There was a difference to the Redicop. So that's how we started. There was some criticism about the fact that we'd funded the project and that the Redicop screen was partially worn. So to SAGIT's credit, they've invested in this testing, and it's come out in this report here. And the results are really interesting, and I think that have a massive impact on how we will approach mill technology design and testing, and so should the whole industry. So this lot of testing was done with test stands and with a range of conditions that's wider than ever been done before. So similarly to in the past, loading up a conveyor belt and adding weed seeds to the chaff and processing it. The change here also was that the flow rate of chaff was changed, so it went from 1.5 and 2 kilos per second, and that represents sort of, in this report it says up to 70 tonne an hour, but I have seen higher chaff ratios than that, so I'd say that 2 kilos a second is probably in the 50 tonne an hour range, so pretty normal to have 2 kilos per second, I would say. And Also, they tested with some worn mills, and they tested with drops in speed. A pretty significant drop in speed, I must say, but I think it's good because it really sort of shows that maintaining speed is pretty important. So this is basically how the testing was conducted. This table here, table 2, is of interest as well. The Terminator screen and rotor were significantly worn, so 25 and 27% weight loss, and the iHSD only had a worn rotor, not a worn rotor and stator. Now into the results. Now, to me, this first table is actually the most significant one. It really hit me between the eyes because this is killing only the background population, so a testing done without any additional seeds added. And in the past, we've always tried to have pretty clean chaff and then just added ryegrass from a seed grower to it. And the reason is just to make it a bit easier to control the variables. And I think that this has really shown that the importance of background populations of ryegrass, because this in-feed rate of 1 kilo a second is that's pretty low, and we're seeing some significant drops in seed kill because the background seeds are lighter than the seeds that we typically get from a seed grower. In this case, the seeds in the background population were about 2.1 milligrams per seed, compared to the seeds added, which was 2.9. And basically what that means is that the seeds in the background chaff, they'd come from a crop. They were a weed in a crop, and they'd been exposed to crop competition, a herbicide regime. They were possibly dormant throughout the season and grew late, and basically not ideal growing conditions for a plant. So similar to what we see in grain, if you have a tough finish, there's the potential for smaller seeds, and those seeds were smaller, and smaller seeds are harder to kill because we're trying to whack them, and when you're hitting them from one side to gain velocity, there's the size or the weight of the seed is proportional to the amount of energy that can go into cracking it and devitalizing it. So the background population showed that big drops in seed kill from what we've seen in the past. The Seed Terminator was still killing over 90%, so 92%. But I think the thing that has got me thinking about it is, well, if this background population of ryegrass was small and hard to kill, how many more populations are there out in the field that are small and hard to kill? So we've started to collect some samples of seed size and try and work out what's going on there. We've already found quite a few samples that are even lighter than these ones, and we're just trying to work out now whether they're actually a viable seed when they're smaller again. But really, really important result and significant for this test. So just going through some of the charts here. This one here is really just showing that the energy used during the test was proportional to the seed kill. And from looking at this, I think that they've taken out the no-load power in this. So this is the processing power. So basically the amount of energy going into the chaff to kill seeds is going to be what actually results in seed kill. And if you are not putting energy into the chaff, you're not going to be killing many seeds. And this plot here is showing the energy for iHSD, Seed Terminator, and high capacity Seed Terminator. As the Seed Terminator is killing more weeds than the rest, it has more energy going into the chaff. The high capacity terminator is going to use a little bit more than the iHSD because it's got an outer rotating row, so the material exits out of the mill at a really high velocity. And the reason it does that is to clear green material. So that's the purpose of that, is that it clears the green material. But it does cost some additional power to have the material exiting and not using that energy to kill weeds. So this plot here sort of shows the challenging conditions all in one plot and shows how the different mills hold up. So you've got iHSD on the left and high capacity seed terminator on the right. You'll note here that they almost behave identically for, these are just the flow rates, the first three, so crank up the flow rate and the kill drops off. The fourth one is a significant drop in RPM and high flow rate, so really when the chips are down, and you can see here some pretty significant drops in kill. I think that 90% RPM is quite low and not common, but it does illustrate the point that that's going to cause a big drop in kill. And worn mills. And then you'll see on the terminator side, we still see some drops in kill with the flow rate, but it's still able to get 90% at the 2 kilos a second. And then still over 80% with a 90% RPM and 2 kilos a second. And the worn was a bit of a drop, but I'll show some photos of the mill there here. So this was the worn mill. I think it had 700 or something hours. And you can see, this rotor really does need replacing. This is the screen wear. The screen's fairly worn. I don't know if this video is going to work. But I think that we will look to investigate when the best timing for replacing wear parts is, because we possibly have been suggesting to run them a bit longer than maybe we should. So again, this is more comparing the side-by-side situations. I think this one makes it the most clear. Figure 4, you've got the terminator up here, able to maintain above 90% kill, even with these small seeds in the background, at the high throughputs, which, like I said, I think that's more like 55 tonne an hour than the 70 that's reported in here. So, your class 9, 10 machines, and then the high capacity terminator and the iHSD are almost identical. I think, I think probably we'll take this result and say that that we really only want high capacity terminators when they're really needed, or if the weeds aren't, the challenging annual ryegrass that we see here in Australia. So if you've got green material, then they're amazing. It's just that we just see much better kill results at high throughputs with the standard terminator. And then a few other results here. This is the mill wear. You can see the change in wear with the mills and the sensitivity of it. Mill speed again. Big significant drops with the iHSD and HD. And then there was a few other mills tested. I I'm not familiar with the iHSD high flow, but that had a significant drop over the standard iHSD. We also have a MIDI mill terminator and a few other variants of that, which is a more compact mill design. And that was slightly lower than, actually no, statistically it wasn't differentiatable between terminator. So, and that one obviously needs a bit more testing to continue with. Manufacturing comments. I guess I will pull up De Bruin on this 27% less power. I think that's a misleading comment because that's actually the processing power and doesn't consider that there is a difference in no load power between mills. The Terminator's got aerodynamic bars, so it's got a lower no load power. So I think that what I wanted to do next was really just talk about whether I could explain the difference in seed kill based on seed size. So I had a bit of a go and dug out the calculations from my thesis. This is available on our website too if anyone wants to dive through the most complicated PhD ever written. But so it's in here under material function. So basically, I exposed seeds to a rotating blade, and I changed the speed and the number of times that the seeds were impacted. So passed them through multiple times and then germinated the result. And then that gave me this curve. So energy on the x-axis and RSE, which is kill, reduced seedling emergence. So that was the kill. And this was 1 impact, 2 impacts, 4 impacts, 8 impacts. And this one over here was 16. So basically, you could kill more seeds by either increasing the speeds or changing the number of impacts. And in the end, I was able to come up with this Mastercurve here, which is this equation here, which basically has some functions for the properties of the seed and the amount of energy that goes into the seed. So when you hit the seed, the energy is proportional to the mass and the velocity squared. So I just used a simple calculation to convert the energy of 2.8 milligrams per seed into 2.1 milligrams per seed, and then compared the kill at those 2 points. So you'll see here at 50% kill for a 2.8 milligram seed, you've actually got 3% kill of a 2.1. So, from half of them dead to almost nothing. So you can see there's a massive impact. But down here where we're operating at, so for example, the testing that we did where the Terminator was 98, 99% kill, if you have a 2.1 milligram seed, we're talking about a drop down to 91. So that sort of explains how it's possible that different seed batches are going to get a different result. And it sort of gets a bit worse. So if you're at 95, it goes down to 82, and if you're at 86, down to 62. So it really falls off the ledge, which really means that, like, to target those smaller seeds, we need to really put a lot of energy into them. So just mapping this curve. This one's the 2.1 milligram curve, and this is the 2.8. So kill here and effective energy. And really you can just see how, if, say we're here at the 98% kill, for a 2.8, it makes sense that like that drop occurs, and that's the sort of drop we saw in this table here. And then you go down to 95, which is what Mike Walsh found the iHSD at, and goes from 95 down to whatever that is, 84, 83. And then, you know, but if you're down here at 85, then you're possibly closer to 60% in 2.1. So it just falls off the ledge a lot faster. So I guess what I'm really saying here is that we, as an industry, have been talking about kill rates and not really, like with different batches of seeds or even different varieties of seed, different types of seed, different, you know, seed sizes, moisture contents, whatever, all of these different things. So they would all have a different curve, but the important number is actually this number along here, which is the effective energy, because I'm sure that we can find some seeds that you could kill almost all of them, which would be the radish in this, you know, in this report, where even if we were down at 8 to 10, that we would kill 98% of them, but we would kill almost no small ryegrass. So to kill small ryegrass, we need to be, you know, in this range, 18 to 20 kilojoules per kilogram. So the unfortunate thing about that is that you've got to use a lot of power to kill small ryegrass seeds. So yeah, that sort of explains what happens there, I think, pretty nicely. And then the other thing I wanted to talk about was what is the kill rate that you actually need to make a difference. So I think there's a few things that go on here. The first one is that, which I think is an important thing going forward, is that often when I talk about harvest weed seed control, particularly where it's not being adopted overseas, is that our weeds shed. And I think the turning point for thinking about this differently was when Josh Lade and I were looking at Steve Shirtliff's results in Canada and wild oats, which is notorious for dropping seeds, shedding seeds, and he really showed that with the chaff carts that they were using to feed cows over the winter over there, that they could really stop the dispersal of weeds with the chaff carts. So what it really showed is that even with a plant that's losing or shedding a lot of seeds, that it's actually the movement of those seeds by the combine that's actually creating the infestation spread and the, you know, more of an impact on the crop. So although the ones that fall you know, may have a big number, those ones that are falling on the ground with the parent plant, you know, they're competing with each other, and in a patch, the ones that go into the combine are the ones, or combine harvester, are the ones that are getting spread, and they're the ones that ideally you kill all of them. So the total control is possibly not quite as important as the fact that the ones that go into the machine, you really don't want to be moving around the farm. But we do still want to drop the total population. So this is what this is calculating, is just looking at, okay, if I capture 80% in the front and I have these different kill rates, my overall control is going to be this. And this 80% can go up and down. So I've looked at, okay, if I have a ryegrass plant, which is 150 seeds per plant, and my chemical control is this one here. So that's 98% control, which might be a little bit high, but I'm not sure exactly what the exact numbers there are. But ultimately, if you get 98% control. And we have these 4 scenarios. So we've got 20%, which is basically, it's doing nothing. It's just collecting it in the grain tank. And then we've got this 48% overall control, a 60% kill rate, 80% kill rate, and 97% kill rate. And then it's just mapping that over the years. So year 1, year 2, starting with 10 plants. And these 2 plots are the outcome, basically. So the first plot is just a different scale to the second one, so that we can see that if you don't do any harvest weed seed control, that, you know, we see the populations blowing out really quickly. And then if you have a 60% control rate, we see an improvement for sure, but it still blows out. And then in this instance, the 80% control rate was a slight increase year on year, so it was slightly out of control, but not majorly. And the 97% control is depleting the seed bank, so that was sort of tipping the scale of the system. But I guess, you know, if we drop this, we see that, so it's only 1% drop in chemical control, and it looks like the 98%, the 97% mill would hold the population basically at 10, just over 10. So that's just holding it. This one's blowing out, and all of these are, so they're all blowing out. So it, you know, and maybe the other way to look at it is if we got 99% and really good control. Yeah, we'll see 99% control. We basically, you only need to do a little bit just to tip the scales. So really, it's super sensitive to how good a control you get throughout the year. But sometimes, in terms of the overall population, it can be the difference between mild increase, mild decrease, or a decrease. It could be the difference between the 97 scenario here, between blowouts pretty quickly and stable. So that's like the whole paddock population, and like I said, that I think that the patch side of things really lends itself to a higher kill rate. So that, I think that's pretty much all I was going to cover. Thank you very much for listening to me rabbit on about all this stuff, and I'll just hopefully get the links to some of this stuff, and keen to have conversations with anyone that's interested. Thank you.